So good morning, everyone. So we will talk today about functional barriers concept and how to design it using modeling principle. So since yesterday or since this morning, we often mentioned about contamination of food by recycled material, cross contamination of packaging, and so. In some design or in some time, we use functional barriers to to ensure some safety of food packaging materials. So the first question, je peux passer. Okay. So what is functional barrier? So as you can see in this schema, here we have the food packaging system with food constituents and multi-layer packaging. We can see here the functional barrier insert behind the recycled materials or any material using unauthorized substances. Not to stop, but to delay the mass transfers of the substances, and also functional barriers can be placed behind all the layers compliant for food contact. This is not the absolute barriers, only temporary. So we need to design or optimize the properties for safe and robust use. Like we can play on the thickness of barriers, the structures of the materials, the chemical affinity of substances between packaging and the materials and food, also the contact conditions. Maybe the barrier can delay the mass transfers after a certain time of contact, but after that, it's no longer safe. So here you have already seen this video yesterday, I think, just to show you the effect of the barriers on the right, on my right, so your left-hand side, we have monolayer buttons, and in the other side we have diffusion barriers. So you can see in the beginning we have less migrations by using diffusion barrier, but after the long contact time, we have almost the same contamination rate because we don't play with affinity, chemical affinity. So as you can expect, we have many type of barriers. The first one is a diffusion barrier. So we play on the diffusion properties. The second one is solubility barriers. So we deal with chemical affinity of substances between materials and food, and we can also, of course, combine diffusion and solubility effect. So we have different results, and we have different kind of barriers. So here I would like to show you the almost famous application of barrier functional is ABA technology. Here the ABA technology is applied for polyethylene terephthalate PET, recycled PET. So here you have the rPET PET recycled, not decontaminated or decontaminated, but using non-approved process. Because if you follow the two presentations this morning, for PET, we need to use the approved process by EFSA for food contact. So here maybe we have the process, but we don't have the whole processes to have them to be to be approved by EFSA. So here we have the rPET not compliant for food contact. To be simple, these barriers is placed between two orders PET. This one is virgin or compliant for food contact, and the layer 8 act as functional barriers. We use here modeling tool to evaluate the safety of the applications. And the question is, it is safe for any food application, or we need to pay attention for some kind of applications. And we use the same principle used by EFSA to evaluate recycled PET. We have many results. We have already published, not yet, is under revision. We have the paper on for the evaluation of PET, recycled PET, published, I hope, soon. And here is one typical migration kinetic of, I think, toluene. So it is the most, the small substances in the challenge test for 4 steps. Because with this kind of trait, we have 4 steps: co-extrusion, thermoforming, set-off, and storage. And as you can see, co-extrusion is really short step, but high temperatures. At high temperatures, we have the how to say, the le sondage, the poll of trade manufacturer, French manufacturers, and they say that the co-extrusion step can be go up to more than 200 temperatures in few seconds. And as you can see, the substances coming from B start to migrate from B to 8. So the functional barriers are compromised. So you are not after few seconds we have already contaminants in the layer 8, and after the set off and storage, the migration starts very rapidly. And here for these applications, we have the migration level after some days, 10 days, I think, exceed the SMN is specific migration limit set at 0.15 ppb microgram of substance per kilogram of food. So this SMN is set for CMR substances. So for sure, we need to, the migration level in food depend on different factors. Here, I would like to show you the effect of the thickness of barrier, so the layer 8 on migration levels. So for 6 substances in the challenge test, I plot here, I present here the concentration in food according in function of thickness of the layer 8. And we can see that migration level, of course, decrease when we increase the thickness of the barriers of the layer 8. But if we increase too much these layers, we go against the principle of reduction of waste reduction, because we increase the mass of packaging. And also if we increase and after we can increase the contaminant amount in the loop of in the recycling loops. And different symbol depend on the chemical affinity of the substance between packaging of the layer B and the food. Here we have many assumptions. We can say that we have the total migrations, or we can have different partition coefficients. That's why we have different values. Because why we put the assumption on the different chemical affinity? Because we have many kind of food products. So depending on the food product, we have different chemical affinity between packaging and substance. So now I will pass on. I will talk about the migration modeling principle. This lectures is already the whole lectures on concerning migration modeling is already published in the platform Fitness 1 and 2. We have also the quizzes and case study. So all you need to understand and use migration modeling tools. So here I just give you some quick principle and some overview of one of. We have several tools, modeling tools. So just to show you one tool, name it SFPP3. So just rapidly, we have, when we put in contact materials and food, we have the migration phenomenon. So all the substances coming from material can go, can migrate into food, and inversely, food constituent also can go into the materials. So as you can see the colorant of the food, we can see the red colorant in your packaging. So the migration depend on the substances substance concentrations, substance properties. So the diffusion and partition coefficients depend also on temperature and time of contact, material structures, material thickness, and packaging geometry. So we need to deal with all of these factors to calculate to evaluate, to calculate the migration event. So if we use migration, it's so long, but if we use migration modeling, we can never have the exact value, because we have the condition of contact are variable, and we don't know perfectly the mechanism, the diffusion and the mass transfer mechanism. So that's why if we fix some thresholds or some limit, we try to use different tiers or different assumptions to get this this objective. So if for the first year, for example, we have the high overestimation factors, if the migration value meet the limit, so everything is okay, we don't need to go further in the calculation process. For sure, if the migration values is higher than the limit, we need to introduce more details or more assumptions to refine the model, etc. Here it's just the summary of all data we need to launch the migration modeling. So concerning substance, we need to know the substance, the identity of the substance, because migration depends on the substance, the diffusion partition coefficients, also the identity of materials, the amount of substance is a material, is the material layers, materials density, the form, the size, the thickness of packaging, also the food type, food product, and food density, contact condition, temperatures. Also, if we can have all of the data, we can launch modeling, and we will obtain concentration of the substance in food. So among all of the data, I will just talk about two properties. This is the most difficult to get, the most important property. So the first one is partition coefficient, called KFP. The KFP is defined by the ratio of the concentration of the substance in food divided to the concentration of the substance in the packaging at equilibrium, at thermodynamical equilibrium. And when we reach thermodynamical equilibrium, that we have the same chemical potential in the two phase. So normally, macromolecule at the macromolecule scale, we cannot have the migration level or migration value more than migration phenomenon will stop at thermodynamical equilibrium. Here, for example, really simple weight and to show the effect of partition coefficient on the migration level. So it depends on we can assimilate with the food type, because, for example, for one substance here, I think is a Yaganov 10776 is antioxidant, is a polyolefin. It is almost apolar substance, and is at the higher affinity with the fatty food. That's why you can see the maximum of migration values. We have the higher migration value for fatty food than dairy or aqueous foods. The second properties concern diffusion, concern the diffusion. So diffusion coefficients is a simple way we can say that the diffusion coefficient is assimilate with the speed of the migration kinetic. So I just come back to the kinetic. This one is a typical kinetic of the migration of one substance into food. So for the first phase, you can see the concentration increase rapidly. So this corresponds to the control by diffusion coefficients, and at the end, at equilibrium, is controlled by partition coefficients. And we have many kind of to evaluate or to measure diffusion coefficient. Here is one simple way, simple but overestimate the diffusion coefficient by using Piringer model. These models depend on three parameters: molecular mass of the substances, the material kind on globe. represented by the tau parameters and also the temperatures of contact. We have the GRC guidance on the modeling, migration modeling, so you can find all of details. Not recently, to already 5 years ago, in one thesis of Pernod Dianzou have studied a lot about the diffusion mechanism of solute on the PET, and she find interesting result that Pyringer model doesn't overestimate in own case. It depends on if you plasticize your material, PET, for example, in contact with fatty product or with alcohol, the TG of PET shift. Decrease, and Pyringer model doesn't overestimate the coefficient diffusion. So if we use this model, maybe we don't overestimate the migration value, and it doesn't obey the principle of when we use a modeling. So here it's just to summarize the all data we need to launch migration modeling in order increasing difficulty. So the first, we need to know material, we need to know about substances, the packaging, contact condition, and after we need to know diffusion coefficient, partition coefficient. And I put here also some of the literature sources if we need to get the value. And I will present you 3 tiers or 3 strategy to calculate the migration of substances from packaging from material to food. So first one is really simple. We consider the total migrations. So it is the worst case scenario for calculations. Everything. Also, the total amount of substances of packaging will migrate into food. So you have the total migrations. It's just a cross calculations, like the concentration maximal, because we cannot have more. It depends on the mass balance. The maximum concentration of substances in food is calculated by these equations, and in some case we don't have, for example, CP0. CP0 is the initial concentration of this substance in the packaging. We can, and if we need to know that the migration does not exceed the SML, is a specific migration limit, so we can calculate the reverse by the reverse weight to get the maximum concentration, the maximum initial concentration of substances in the packaging. And we can ask if our suppliers, etc., if they can guarantee that, ensure that this concentration in the packaging is less than this value. And the second strategy is the migration controlled by partition coefficients, because as I said before, we cannot go further than thermodynamic equilibrium. So just the equations is just a little modified, and don't be in the case of the ratio of mass of food divided to the mass of packaging is always large, and if we have the big partition coefficient, KFP is bigger larger than 10, we don't have the significant effect of K. So it's coming like it's become on the total migration assumption, the first strategy. And in the same way, if we need to know the maximum initial concentration of this substance in the packaging, we can use these equations. And the last one is we introduce all the assumptions, and we use the detailed modeling. So we have some assumption that we have the conservation of mass. We use monodimensional modeling. We don't have reaction between substances coming from the material, because sometimes we have the breakdown product or reaction product. So this tool doesn't cover it. We have the thermodynamic property according to Henry law. So that means that concentration of the substance is really low. We are at infinite dilutions. We have the transport property are constant is the same step, and we don't have the modification of material intrinsic properties. So that means that if you observe that we have the plastification effect phenomenon or effect, we need to consider different steps. As I say, that we have many tools, modeling tools available in Europe, free open source or not. And in our case, we have two tools developed by INRAE. SFPP3, we have the interface and the software, so it's easier and more friendly to use, and also we have the FMecha engine. It's not available on MATLAB or Octave. So and we can see here many guidance to help you if you need to go further. Also to be with SFPP3, we have three. We have three platforms in French or in English. So in English, it's a fitness project, of course. And in French, RMT Proper Food is a platform who propose you some case study and also the lectures on the migration modeling. So just rapidly to show you the software SFPP, Safe Food Packaging Pattern, in this link. So to launch the main interface of SFPP3 tools, so just to get access of this tool, you need to send us the message, because we will give you the login as a password. It's free, but we need to know who you are, and to prevent some attack. And so the main interface, you can see here, we can find contact conditions, data concerning layers or material layers, and here each time when you put in the case, you have some help or information about this. Don't forget that this tool also host the big database about the migrant and transport properties. So if you click here or here, you can find some interesting information. So just to go in the detail, for example, for contact conditions, you can see many data concerning the dilution factors, partition coefficient, volume of food, surface of contact, etc. Also is the same kind of for the property of materials. So you can see the thickness of materials, the density, partition coefficient, diffusion coefficient, and also the initial concentrations of the migrants in the layers. And for sure, here you can see the layer ones, but you can also launch the simulation for multi-layer packaging. And now it is really for the interface of the result. So we have many sheets. So the first one is the curve concerning the migration kinetic or disruption kinetic, because substance quit the packaging, go into the food. So it's a disruption phenomenon. And after, you can have the simulation report. You can have also the profile, the interactive profile. That's all for today.